Hey physics, welcome to another flipped lecture. We're going to be talking about refraction today, similar to reflection, but not. Now, instead of talking about light bouncing off of an object, we're going to talk about light going through an object and changing direction. This is review from physical science. You did talk about refraction already, so hopefully you can recall much of this. We're just going to add some math to principles you already know. Refraction is caused by a change in the speed of light. Light travels at a constant speed in a vacuum, but when it starts to travel through various media, it slows down or speeds up depending on what we call the optical density of that material. Another way of looking at the optical density or how much something slows down light is talking about its refractive index, another word for the same thing. And so we can calculate the refractive index if we measure the speed of light in a material, which is challenging, but it can be done. And if you measure the speed of light in a material, then you can compare that to the speed of light in a vacuum and get its refractive index. You could also just measure its refractive index and use the same formula to calculate how fast it's going in that material. So that's the more common application of this. Refractive index is easier to measure than the speed of light in a material. But here we have this relationship here that n, the refractive index, is the relationship between the speed of light in a vacuum and the speed of light in a medium. And when we compare those two, we will get a decimal number, a relationship, a ratio, and that is the refractive index for a particular material. That refractive index will determine how a wave of light will change its direction when it moves into that new substance. So we've already covered this in physical science a long time ago, but just to remind you, this is refraction. Refraction is an image getting distorted because of light. You can see that in the straw, or we could just look at the light bending as it goes through a material like the block of plastic. So again, you're seeing just the straw through light here. I'm sorry, through air here. Here you're seeing the straw through air and glass. And when the light changes medium, the image gets distorted. The image bends, the light bends. And then here it bends even more because it's going through not just one medium change, air and glass, but through two medium changes, air, glass, glass, water. And so the light is bent even more and the straw is even more not where it looks like it is. And so you can see that light is bent, you can see that light is bent, and that happens anytime light changes medium. And it has to do with the speed of light altering as it goes through those different medium. And light bends. How does it bend? Why does it bend? That's kind of funny. Well, think about a car driving down a highway and you are not paying attention and the side wheels, the right wheels, get onto the rough shoulder of the road. Maybe it's muddy, maybe it's grassy, and when the tires get in there, they slow down. They are grabbed by the higher friction of that material. And so those tires slow down, these tires are still going fast, and so the car turns and winds up going into the rough patch. And that is something that you will experience as you're driving down the road. If you ever do wander into a significantly different material with half of your tires, the car will turn into that material. And so that is one analogy for what happens when light, a beam of light, enters a new medium. Is it slows down first on this side, and because that's the first side to get into the slower material. So it's kind of turned towards the slowing down. Okay, this side is still going faster, so it spins kind of. Now, light is not a car, but the analogy helps us understand why. Part of the beam of light slows down first, and it bends the beam of light into the material. Okay, so how can we measure this? Because physics is all about math and all about measuring, and so we must be able to measure this phenomenon, right? Just like reflection has a normal line and you measure incidence and reflection angles from the normal line, the exact same thing is going to be true here, only the reflection, it stays on the same side as of the mirror, right? It bounces off. Now in refraction, we're talking about something going in, but we still have to draw a normal line, and the angle of incidence and the angle of refraction are going to be on opposite quadrants of the intersection of the boundary layer and the normal line, but we're still going to be measuring everything from the normal line. Okay, so the degree of refraction is a function of the relative indices of refraction, n sub I, the medium of incidence, where it's traveling first, and then n sub r, the index of refraction of the refracting material, the thing it hits second. Okay, for the two medium involved, and the angles of incidence, theta I is the angle of incidence, again from a normal line, and then theta r is the angle of refraction from that same normal line, but now in the opposite quadrant. You'll see a picture in a minute, it'll make sense. This mathematical relationship, n sub I times the sine of theta sub I, equals n sub r times the sine of theta sub r. So the index of refraction in the first medium times the incidence of the angle of incidence from the normal line in the first medium is equal to the same quantities in the second medium. And that's called Snell's Law. And so again, we measure everything from the normal line, and if we curve the boundary, then the normal line is still at a 90-degree angle to the point that the light hits it. So if we have a flat substance that the light is passing through, and we have a normal line that's perpendicular to that, then it's a nice normal crosshair kind of coordinate system. But if we are curvy and the light hits here, now our normal line goes like this. But if the light hits here, now our normal line is like this. If the light hits here, now our normal line is like this. It's always 90 degrees perpendicular to the point where the light hits the surface. So the curvy boundary layer greatly affects where the light ray winds up going through the second material, and you'll see examples of that here in a moment. Here is a simple situation where we have a straight boundary line, we have light coming in from the left, and the angle of incidence, here they just put I, but that would be theta sub I, right? It's being measured from a normal line, which in this case is horizontal. And that light ray hits the boundary and then refracts. It goes into the second material, but notice it's not going straight anymore. It turned because N2 is more optically dense. It slowed it down, and it turns towards the normal line. And that's something that will help you check your work in this part of the chapter, is if the second material is more optically dense, has a higher indice of refraction, then you should see the light ray go toward the normal. And if the second material has a lower optic density, a lower indice of refraction, you should see the refracted light ray go away from normal. Okay, so here the line, this degree is greater than this degree. It's coming in and it is turning towards the normal in the new material. Okay, let's do a little math with this. So the incident ray is going to be 30 degrees, theta sub I, and we're in air, which has an index of refraction of 1. And then we're going to be going into water, which has an index of refraction of 1.33. It's more optically dense. It slows light down. And so the sunlight comes in, hits the water. Here's my normal line. My initial angle is 30 degrees. What is my index of refraction? I'm sorry, what is my new refracted angle down here? So N1 sine theta 1 equals N2 sine theta 2. Put in everything I know. N1 is 1. N2 is 1.33. Sine of theta was 30. Sine of 30 is 0.5. 1 times 0.5 is 0.5. I don't know my second degree. That's what I'm looking for. So the best I can do is 1.33 times the sine of theta. So I just carry that through here. And now I'm going to get rid of the 1.33. I'm going to divide both sides by 1.33. And I have 0.5 divided by 1.33 is 0.376, which is the sine of theta 2. So I need to take the inverse sine of both sides to get theta 2. Inverse sine of 0.376 gives me 22.09 degrees. And if I were to check my my significant digits, actually this is not the way I would want this expressed, because I gave you one significant digit here. So you should just say 20. This is an example I stole from a book, and they don't care about sig figs apparently. But this at least shows you the math. Okay, pause here if you need to look at that again. Here is an example for us to do together. A woman shines a laser into a pool at a point 8 meters in front of her. Her hand is 1.7 meters above the surface of the water. The pool is 3 meters deep. What's the angle of refraction inside the pool? I'm looking for theta sub r, just like I was looking for it in the last example, but I'm going to make you do a little geometry first here, just to remember, because geometry is fun. So we have a right triangle here, 1.7 meters and 8 meters, and I need to know theta I, which is not this, it's the complement of that, right? Okay, so what I need to do first is do a little bit of trigonometry to figure out what this angle is, and then I can figure out what that angle is. So tangent of 1.7 divided by 8, tangent of x is 0.2125. So if I take the inverse tangent of both sides, now I have that x is 12. So if this is 12 degrees, then this has to be 78 degrees, right? Because those two are complements. So now theta sub I is 78 degrees. And here, again, air has a refractive index of 1 and water has a refractive index of 1.33. So here we go. N1 sine theta 1, N2 sine theta 2, or if you want to use I and R, it's the same idea. 1 and 1.33 are my indices of refraction. Sine of 78 is 0.9781. I don't know this, so I can have to just leave it this way for right now. I'm going to divide the 1.33 out from both sides. So I get 0.7354 equals the sine of theta. Take the inverse sine of both sides. Theta r is 47.345 degrees. And so that is my answer here. That's the indice of refraction. I'm sorry, that's the refracted angle. Okay, that's the kind of stuff you'll do. It's not challenging. I think you'll do just fine. If the angle of incidence is greater than a given critical angle, which we will call say theta sub c, then light doesn't refract, it reflects, and we call this total internal reflection. This is used in fiber optics. So you have a glass wire and you shine light down the glass wire, and the light could just come out of the glass wire. But because it's going parallel to the fiber in the glass, it's going to bounce at very extreme angles off of all of the surfaces because it's basically parallel. So it's just going to kind of skip across. And when it hits at those extreme angles, it doesn't get to come out of the fiber. It gets reflected back down. And you'll see why here in a moment when I show you some examples. But we use this because light through a glass is faster than electrons down copper. And so we can send more information faster down a light wire than we can with an electron down a copper wire. And so sometimes these are called light pipes because the light can't leave the fiber optic. We use it for other things as well. You'll notice this if you ever go diving, you're scuba diving, and you're deep enough under the water to look kind of at an angle at the surface of the water. You will not be able to look out at daylight. You will see a reflection of the ocean from the surface of the water. So, and I'll show you an example of that here in a moment. But if you have a light source going straight up inside the water, and this is air, it will go out and escape. And at small angles from the normal, it will still escape. But as the angle from the normal gets bigger, there comes a point where the math makes this sine, the sine of this angle greater than what it will take to get out of the water. It turns it and brings the light back into the water. And so now any angle greater than that, light just reflects. The refraction loss turns it, and turns it so much that it brings it back into the water. Okay, so this is called total internal reflection, and we use it again in fiber optics. And as I was saying before, the light coming down the pipe bounces at angles greater than the critical angle and stays in the pipe, even though a light beam could conceivably come out of the pipe. It never strikes at that kind of angle, and so it stays in the pipe, the light pipe. And we can use these for communication at very high speeds over very long distances. Okay. Here we have an example of total internal reflection as well. You're looking through a glass of water at the Sydney Opera House, and you see the Sydney Opera House just refracted through the water in the top. But in the bottom, you're actually seeing a reflection of the refraction. This image bouncing off the meniscus of water up here and coming back down to your eye, and you see the Opera House twice. And that's another example of total internal reflection. Okay. One last concept, and that is dispersion. Light bends not just because of its speed difference, but if we were to go a little bit more into detail of refraction, we would have to include the wavelength of light in our math. I'm not going to make you do that in this chapter, but just know that that does influence it as well. So wavelengths that are longer don't bend as much as wavelengths that are shorter. And so the greater amount of, the greater wavelength influences a greater amount of bend. And so what we do here is with white light that has lots of different wavelengths of light in it, when the white light is bent, is refracted, it actually spreads out, and we get different colors getting turned a different degree, and we call that dispersion. That is what happens in a prism, and that's what happens in water droplets and makes a rainbow. Okay, so obviously rainbows are important to us in Christian faith because God chose to make that a reminder for us of His faithfulness and His love. And the rainbow is caused by water falling through the sky, water droplets. It's raining, or there's at least a heavy mist out there. And as the water droplet falls through light, it refracts and reflects that light back towards us. And you will see a rainbow 40 degrees to 42 degrees from what's called an anti-solar line. I'll show you a picture in a minute. But if you're standing with the sun behind you and a rain in front of you, draw an imaginary line from the back of your head to the sun. That's the anti-solar line. And you're looking down the anti-solar line. 40 degrees to 42 degrees from there, you will see a rainbow. And that has to do with the angles of refraction that come out of a water droplet. If there's enough moisture in the air and enough light, then you can actually see a second reflection within the water droplet at about 51 degrees and see a harmonic of the rainbow. And I also have heard that it's possible in large enough water droplets, if it's really coming down out there. I've also heard that it's possible to see a third harmonic. I've never personally seen it, but I've heard that that's also possible. So you can see maybe 3 bands of rainbow. Anyway, that's because light is scattered. It's dispersed because of the different wavelengths of light. When they get bent differing degrees. So that causes rainbows, right? Here's a prism, and light is being dispersed once and twice. And because it's being dispersed twice, and because the angles here of this prism are not parallel, then the light gets spread out as it comes out, and the red is not bent as much as the purple is bent, and so we get this rainbow leaving the prism. Okay, same thing happens obviously in water droplets, but the water droplet, it gets bent and then it gets reflected by the other end of the water droplet. This is the total internal reflection phenomenon. And then as it gets reflected, it's bent again, but now it's upside down as it comes out. But we don't see the purple on top, we see the red on top, because it's the water droplets up here that are shining their red light down at us that we see. And then it's the water droplets down here that are shining their purple light more up to your eye. So you see the rainbow this way, but it's actually leaving the water droplet this way. Here's that funny anti-solar line, a line from the back of your head to the sun, and we will see red light at 42 degrees from that anti-solar line, and you'll see violet light at 40 degrees from that anti-solar line, and that just helps you imagine what you're actually seeing. Okay? And of course, God gave us these. Obviously, the phenomenon would have existed if God had not chosen to make it a symbol. But he gave us a meaning to this symbol to remind us that he will never again destroy the earth with water. The next time the earth is destroyed, it will be with fire. And we can read all about that in the book of Revelation. But here again is just a symbol of God's love and faithfulness and his long suffering towards sinful humanity. And we can see it in all kinds of places, even in contrails from jets. So anytime you see it, you're seeing a physical phenomenon and a love letter from the Lord. God bless you. Have a wonderful day. Talk to you.